Every weld you make is more than molten metal and filler wire. It's metallurgy in action.
So, what is metallurgy? Sounds like a big science word.
Metallurgy is the science and technology of metals, how they're extracted, refined, processed, and alloyed into the materials we use every day. Whether you're welding steel, stainless steel, or aluminum, the metal's internal structure determines how it behaves under heat, stress, and load in its intended application. Metals start in the earth as an ore, or an oxide, part of a rock. After refining, we get pure metals like iron, aluminum, copper, nickel, titanium, and others. But most of what we weld are alloys, mixtures of metals with other metals and even nonmetals designed to improve the strength, hardness, corrosion resistance, or toughness of the material.
Have you ever thought about what distinguishes metal from a non-metal? Well, those are good questions. Perhaps you've considered it before, and even if you really haven't, many of the traits are obvious given the things that we are used to seeing every day. When we think of metals and what we know and use, color and luster may come to mind. That's right, the unmistakable gold, silver, or copper of the shiny objects that we see and use every day. Metals are generally malleable, some more than others, more so than nonmetals. That means they can be formed into shapes and they'll retain that shape for the most part. Metals are also good conductors of heat and electricity, hence their use in heat exchangers and for electrical wiring. Again, some are better than others, but all are better than non-conductors or insulators like rubber or glass. Metals have a high density compared to non-metals, say plastics or ceramics. That means for a given size or volume, there's a lot of atoms in there, so they're dense and heavy. And again, this is a broad range statement considering the extremes. For example, aluminum is 1/3 the density of steel, which makes it a lot lighter in terms of pounds per cubic inch. And lead is approximately 1/3 more than steel. So it's a relative spectrum compared to non-metals. Metals have high strength and hardness, which you've surely noted. We use metal fasteners and structures because they're stronger than alternatives. Most metals are solid at room temperature, with the exception of mercury, which is usually more dense than lead, by the way. Another key aspect of metal properties is that they form an internal crystal structure at a microscopic level when they solidify. This is the orientation of elements and molecules in the metal or in the metal alloy. Heating and cooling can change the crystal structure and the location or distribution of elements within that structure. Heat causes things to move around inside, even if the metal isn't fully melted. And the rate of cooling determines what crystal shape it will return to. This is the fundamental concept of heat treating a material. Metals also have chemical properties. So, yes, chemistry is important in welding, but you don't have to be Dmitri Mendelov or memorize the periodic table unless you want to. And it seriously wouldn't hurt to study a little basic chemistry. Metals are typically positively charged, meaning they have room for electrons, and opposites attract. So the positively charged metal attracts a negatively charged electron, and hence metals can receive or emit them. A key to being a good conductor is moving those electrons around. Because metals are dense, meaning the elements and atoms are very close and compact, they're very good conductors of heat. Again, this is relative compared to nonmetals. Think about nonmetals or insulators like leather gloves used for welding. We'll talk about these topics throughout the modules. Another notable factor is that metals like to form oxides, where they share electrons with oxygen, turning out and ending up as rust on steel. And you might think that stainless steels don't form oxides because you don't see any rust on them typically. But the truth is, all metals form oxides, except for the noble metals like gold. The trick is, stainless steel forms a chromium oxide as a protective layer instead of an iron oxide, which we all know is rust. So if you're wondering how the heat of welding can affect the properties of stainless, stay tuned because that's exactly where we're going. Mechanical properties are important metal characteristics. When we discuss mechanical properties, we're referring to things like strength, which is the resistance to a load or a stress that would cause strain or a movement as a response. Think of all the different stresses or loads that could be placed on an object. The direction of the load is a fundamental consideration to defining how strong that material is. Here are some common general load types: tensile or pulling in opposite directions, compressive or pushing against an object, torsion is a twisting load, a shear load is a load that's parallel to the material's surface, and a bending load or moment, which is a perpendicular load or an unevenly applied compressive load with forces pushing up and down. These are often defined as standard material tests that can be done to determine a material's performance under each load condition. To complicate matters, loads can be static or constant, or they can be dynamic and cyclic, where loading and unloading occurs frequently. As you might imagine, dynamic loading is more severe and requires many different considerations. Elevated factors of safety, ongoing inspection and monitoring, such as with bridges. Tests that apply these loads are used to evaluate the various characteristics of a base metal, a filler metal, and resulting weld metal. Hardness, which is the resistance to indentation, scratching, or abrasion. And hardenability, which means something slightly different. This refers to the ease of hardening a material. In the case of steels, it refers to the ease of quench hardening a material. It can also refer to the maximum attainable hardness in terms of ranking groups of metals or metal alloys. Ductility is the ability of a metal to stretch, to form and deform without breaking or tearing. Toughness is the ability of a material to absorb energy, such as during an impact. And elasticity is a condition that allows material to retain or to reverse to its original shape when a load or stress is removed. Plastic deformation occurs after the point of elasticity, where deformation is now permanent, and when the load is removed, it will not return to its original shape. As we'll discuss, this is also called the yield point, the point of no return. And normally we use this as our design limit with varying factors of safety. And that makes sense, right? We want to design to the safe point, the point at which no permanent deformation has occurred. These are important concepts to understand when you're dealing with metals and designing or fabricating.
Inside every metal is a crystal structure, a repeating pattern of atoms. This structure changes when the metal is heated, cooled, or alloyed. Metals also come in two major forms: wrought alloys, which are rolled or worked into shape, and cast alloys, which are poured into molds. Metals and shapes can also be 3D printed. Each form behaves differently under the heat and stress of welding and based on the chemical composition of the material. Heat treatment changes a metal's microstructure. Annealing is a softening process. Normalizing refines the grain size or the pattern of solidification. Quenching, in the case of steel and most metals, hardens an alloy. Tempering reduces brittleness followed by quenching. These processes matter because welding is, in many ways, an uncontrolled heat treatment, and the metal responds accordingly. One of the most important properties for welders is thermal expansion. Metals expand when heated and contract when cooled. But welding doesn't necessarily heat and cool things evenly, does it? The arc is a highly localized, uneven heating source, traveling along the weld joint. And that uneven heating and cooling causes distortion, weld shrinkage, and residual stresses that build up in an assembly. If you've ever put two pieces of metal together and they look like a potato chip when you got done, you've seen thermal expansion and distortion firsthand. Understanding metallurgy and the properties of metals will help you predict how a metal will behave when it's welded. Will it distort? Will the heat affected zone harden due to rapid cooling or soften due to over annealing? Will it crack? Will it crack through the weld or will it crack under the weld? Will it lose strength? Metallurgy gives you the tools to control the weld before you go in to strike an arc, not just to react after the fact.
Now, that all leads into welding metallurgy, the part we're focusing on here. This branch of metal science is concerned with how metals behave when welded. The heat of welding and many related processes has the ability to change mechanical, physical, and chemical properties of common everyday metals, not to mention those that are highly alloyed.